So we looked at histogram. We'll look at trying to do the same thing with a histogram, but we're going to instead plot density function. Okay, it's called probability density. Okay, probability density, and I'll try to explain as to what it is. So basically, what it does is it takes this is basically, if you add it all up, it adds up to 1. So this multiplied by this bar, okay, the range of this thing is going to, so this level multiplied with this range plus this level multiplied by this range plus this level multiplied by that range, and so and so. If you sum it all up, it's going to give you 1, okay, which is 100%. Okay, so what this tells us is what percent of your data in that column, in that lone size distribution, in that lone size column, what percent of the total data is going to fall in that range, what percent in that range, and so, right? Let's try to sort of make sense of that by reducing the number of bin count. Okay, so we'll take only 10 bins. Okay, so we're going to plot the same data but now with 10 bins, and if you look at it, of course it's going to jumbled up. You see the distribution is already looking different, which is not the point. What we're trying to say is what we're trying to do is, okay, within this band at 0.00005 multiplied by this band, okay, which is what we are doing. So this is around 5,000, right? This is another 5,000. So we are multiplying this individual band, okay, and if we add it all up, you will see that it adds to around 1, okay, which is 100%. Okay, it should be technically exact 100%, but it is 1. So that's doing the same data. Instead of count, instead of frequency, you're doing density. Okay, probability density. Okay, probability density. Now, so we saw there was a problem with histogram, right? In considering, we need to consider the width of the bins, and depending upon the size of the bin, the width of the endpoints you pick, you can get a completely different picture of what the underlying data looks like. Okay, which is not a good idea, right? So you want to sort of get what is exactly going on. Okay, and there are some notes at the back, at the tail end of this thing, that you can read up on some of these references. Okay, if you want. Okay, but we were here. Okay, kernel density. Okay, and so kernel density estimators are basically it's a class of estimators where they can actually look at the data and plot the exact distribution, or very close to an exact distribution. Okay, now the exact math you can read up on those two notes, but if you don't want to be bothered with the math, all you care about is getting the right distribution or the right right feature within the data. You can sort of use this dist plot. Okay, but instead of KD equals false, because here we said KD equals false, we are going to remove that. So it's going to plot the density estimator. Okay, we can get rid of the histogram column, just look at the distribution. So this tells us how the distribution looks like. Okay, and this tells you that it is not a normal distribution, right? The Gaussian distribution. It has a long tail. Okay, so some of these features you can sort of extract from this kind of information, right? Now you can look at this shape and say, it looks like a certain distribution I have seen, right? So, and if you want to, so there is something called parametric and non-parametric. I don't want to get too much into that, but there's something called parametric and non-parametric distribution. Parametric distribution would be where if I were to give you a mean and a standard deviation, you can create the distribution from just those two numbers. Okay, so you don't care about the underlying data. As long as you know the mean and the standard deviation, you can come back and recreate that distribution. Non-parametric is something where you don't have those numbers, right? So it's basically a lot more custom distribution, right? And this one looks like a custom distribution, although you can try to fit. We are going to import this library called stats, okay, and we're going to fit a gamma distribution, right? So if you can look at this, you can sort of say that, okay, this one looks like a gamma distribution, okay, because it is skewed one way, right? And then once you fit a gamma distribution, you can extract the parameters of a gamma distribution. You can say that if I were to give you these parameters, you should be able to conceptualize as to what the data looks like, okay? So that's one more reason why you can sort of fit a custom distribution, as long as you have a good confidence that whatever parameters you're going to extract out of this distribution, you can use it later to recreate the data set, okay? So the goal is that you can take a few parameters and recreate the underlying data set, or you can recreate the underlying lone column, for example, right? Approximately, okay?